Oh, no, 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 you're good. I want to be right, like, in the I have my physics got it already. I'm also going to be watching the Slack to answer technical questions. All right. I can maybe help.
Okay. Yep. Everybody.
I can do that. It's fine if we enter. Yeah. Also, people may. Like that. Okay. For people that like broad stuff. Right, exactly. I guess you could like have to make it. Look at the Google out in the Slack, right? Ulysses workshops. Yeah. I pinned at the top where it used to say like agenda. I pinned it. Yes, my laptop.
So make sure that your audio is disconnected so that we don't get looped back.
Yep, I think it's
Looks like it.
I didn't connect to the audio on the WebEx.
You did not
Want me to stop?
stop for a second.
You go ahead. You know this better than me.
Yeah, connection. Yep, that's good.
Perfect.
That's good. So are you sharing your screen or
Yeah,
just
just a
app?
screen to
Okay.
make it easier.
All right.
Perfect. Thanks, Thomas.
You're welcome.
And we were going to use just this mic. Do you think that's fine?
Um,
Or should we use?
At times when you turn your head, it may not. This is better because you
Okay.
can move around, just gives you more freedom.
Okay. Well, we're going to be like here mostly, so that's why we were thinking just
Is
using
it
that.
just you or is it?
It's the three of us.
Yeah.
You also got the handheld. So the people remote when you move your. they may
Okay,
not hear
okay.
you right, yeah.
Yeah, should be fine. We can
Just
do
stand on this side of the microphone when you turn your head.
that. Sounds good. Sounds good.
And we've got two of these, so one.
Yeah, okay.
Yeah. I don't know unless someone took the other one to the bathroom.
Yeah. Is it still under there?
No, it's in here.
Okay.
Yeah, it's here.
Yeah, I was using the. All this will go
everyone. We're gonna get started with the hands-on session. And I know Drew or Rachel have already posted some instructions to set things up on the Slack general channel. But I think if you haven't done that, that's okay. We can do it now, right? Yep. All right. And people on that should be able to follow along because Drew's going to share her screen and everything is on Slack or via oral instructions here.
Yep. Okay, so hello again. You saw me yesterday. I'm Joe Taylor. I'm the lead of the Ulysses Data Products team. I'll just be giving like the introduction to this session, and then Elaine Frazier and Rachel Plesha will take it away. Rachel is the deputy of the Data Products team, and Elaine is a member, and all three of us have been on the Ulysses project since the inception. 4 years ago? 5 years ago? Yeah, something. Okay. Okay, yeah, just wanted to flash this again because I'm really proud of our team. And if you see any of us here, feel free to say hello. Okay, really briefly, I'm going to give you a refresher on the data products, which I went into a little more detail yesterday. Then you're going to hear from Rachel about how to use our Ulysses search form in a little more detail. She will then go through a walkthrough of our co-added products. Then we're going to switch to Elaine, who will show you a walkthrough of our time series products and our WFC3 drizzled images. And then finally, depending on how much time we have left, I'm going to show you a brief introduction on how you could programmatically download both HLSPs and the constituent HST data, co-add your own spectra, create your own time series spectra, or create custom calibrated STIS spectra. So really quickly, here's the promised data products refresher. This is just a modified slide of what I showed yesterday. And really the important thing to note here is these 6 HLSP types. You're going to hear us refer to these as different levels. It's just a different type of product. Our level 0 products are the custom calibrated spectra. Level 2 are our co-added spectra. Level 3 are abutted co-added spectra. That includes the same instrument and resolution regime. And then level 4 is our abutted co-added spectra for all telescopes, instruments, and gratings for a contributing target. And then level 5 are our time series spectra, and level 6, the WFC3 drizzled images. And you're going to see how we create different products based on the observational configuration and the variability of each target. There are a couple links here to our code databases, including the Ulysses Python package and the utilities package. I think these slides are in Slack, so if you want to click on the links, you're welcome to here. And then finally, just some ground rules for the hands-on session. We ask that if you have any verbal questions to please save them for the end of each presentation. However, you can post questions in the data products Slack channel at any time, and whoever's not presenting at that given moment will try to answer your question in real time in Slack. And I've also heard a few questions from people already. Do you need to run the notebooks in real time with us? No, you don't need to. You can just follow along and watch and treat this like a normal presentation. And if you're having any trouble with installation or running the notebooks yourself, feel free to ping us and we'll help you troubleshoot afterwards to save time during the presentation. I think that's it. So, Rachel, you're up. Do you want me to just close this? Sure.
Okay. Hopefully people can hear me. I hope so. It's green. Okay. Awesome. So, hi everyone. I'm Rachel Plesha. Before we get into kind of the meat of the session, we wanted to first just give a quick live demo of the catalog, so nothing's going to go wrong. So Joe showed this yesterday a little bit, and so I just wanted to show a few more features and just show how hopefully easy it is for everyone to use. So this catalog is very similar to the Hubble and JWST mission mast search forms. And you can even get to it if you're on those by going to this button here up at the top. And you can see that there's the Hubble and Webb search form options, but then there's the HLSPs. And if you select that, that's where the Ulysses search form lives. So you don't even have to have this bookmarked. You can have it bookmarked, but it's really easy to get to even if you don't know. And on the search form, there's lots of different, or there's very similar search criteria to the Web and Hubble search forms, such as objects, from where you search the name RA or DEC, and you can resolve or unresolve that with Simbad, just like you can on the normal Hubble and Web search forms. But we also have very specific search criteria on this page to Ulysses, that we've collected a lot of metadata for all of the different targets. And so we wanted to be able to parse that itself. And so the first one I want to highlight is this contributor column. And you'll notice that if you hover over anything, there's more information that you can figure out what that column means as well. But so by default, Ulysses is selected, but soon we'll have XShootU and Penelope also available through the search form. And so you can select that and unselect Ulysses, and what that will show you is all targets that have XShootU data. So there are Ulysses targets that don't have XShootU data, and so if you only wanted the targets that have XShootU data and Ulysses, then you can just select this XShootU button. And the same thing for Penelope. We're hoping to get those very soon, so just be on the lookout for that. There's this very similar buttons down here where you can select the observatory. So if you only wanted data sets that have fused data, you can just select just fused. And I'll just draw your attention down to this very bottom, which you probably can't see, but maybe you can see up on the other screen, where it says filtered results. And so you can see that there's 161 targets out of 508 that were found when we're just looking for fused data. If we then incorporate HSD as well, that should go up to 508, yeah. So at any point, if you decide you've made a mistake, you can just click this clear form button here at the bottom as well, and that will reset everything back to default. So there's more search criteria that we won't go through, but it's very similar to Hubble and Web as well for grading and start date times. And what we really want to focus on here is this additional column down here where you can search for the different metadata parameters. So for example, if you wanted to search for spectral type, you can start typing that and it pops up and you can select it. And say we want only B type stars, and so we can do B wildcard. That just grabs all of the B stars. You can put in a very specific type as well, and that should work, hopefully. We won't do it live, just to be sure. But you can see that that's filtered down to just 86 results with the spectral type. And then if you want to just add another criteria, you can just add another column there. And then if you decide, oh, actually B type stars are fine, I don't really care, you can then remove this condition with this X. So that's how all the options, some of the options that you can search for on the form. But there's also this box down here that allows you to decide what you want to view when you use this search form. So we have a list of recommended search criteria that we say are good to search for, but you can also search just like that. If you say you want to know if the data has XShootU or Penelope data, you can add the contributor column as well. And you're also able to select all columns to be visible just with this button right here. I don't know can people see that in the back? Okay. Yeah, so you can select this button here. If you decide, no, that's way too many columns, I don't want that many, you can just go back to selecting recommended. Something just to note that's a bug that we just recently found is that if you select all and you press search, it's actually not going to show anything. And that's just because of a weird interaction with plot preview and HLSP name. So if you remove one of those two columns, then you're able to search for everything. We hope to get this fixed, but just know that that's a small bug right now and you're not doing anything wrong. Okay, so. Those are output columns down here at the bottom, but then you can search for those as a condition here. Yeah, here, I'll show you what. It does. So if I select everything and press search, it says no data are available, which is not true. So that's just what's going on. We just need to fix that. There actually are data, just right now I'd recommend probably just typing in whatever additional column you want. So if you wanted the contributor, then you could type that in as well. Just don't type in HLSP name, because then that will break it. So it's just a silly bug. We're always finding new bugs. But that should be fixed hopefully soon. So for this search, I completely missed this, of course. So this is a really great feature as well that we can select based off of target type. So if you only wanted stars in the LMC, you can just select LMC. If you just wanted T-Tauri stars, you have to click T-Tauri stars and then unclick LMC. It makes you click something. You can't not click nothing. And so for this search, we're just going to look at LMC stars. So we can see that filtered down to 182 stars. And we can just press this orange search bar down here. And this is what the output data should look like. It should not say no data available. This is what it should look like. And then just to draw people's attention, Joe mentioned this yesterday, but everything in orange is a hyperlink. And so the Ulysses name column links to Sinbad, so the Sinbad page for that target, just for convenience. And then all of the information's magnitudes and masses and such links to the reference paper that value was derived from. And then the last hyperlink on here that's showing right now is for the preview plots. And so these are quick look figures that are fully interactive. And so these are just to give you a quick idea of what the data you're going to download looks like before having to actually download it. And so you're able to zoom in on different regions, look at all of the cool lines everybody's been talking about. You're also able to toggle on and off different spectra. So if you wanted to see, you didn't care about the level 4 spectra and you wanted to just see the other modes, you're able to do that. And so you can toggle on and off however many you want. You're also able to switch to be log scale, which is particularly useful for the T-Tauri stars. You can download the data as well. This will download whatever is on the screen. And yeah, there's a lot of cool things that you can do with this plot, and we have a page on our website that fully documents how to walk through these plots if you're unfamiliar with Plotly. But yeah, they're meant to be here for you as just a quick look without having to download any data, although it seems like everybody's looked at all of the data. So, so if we go back to the search form now, let's actually download some, we'll pretend to download some data. So we'll select a couple of targets. The first thing I want to mention is that there's this export table that you can select all rows, so it will give you an information of all of the metadata that you've selected of the columns that you want to output. And so this is useful if you just care about the metadata and you don't actually want any of the downloaded HLSPs. You can do that for all of the rows, or you can just do the 2 rows that I've selected. So that's an option if you just want the metadata. But if you want the actual FITS files to download, you can go to this download selected data sets, and then there's more options. So there's these 2 quick download buttons. And the first one is just downloading a folder with all of the files contained inside of it. Or there's the quick API script, which is a terminal line script that you can just do a curl command and it gets all of the data down for you. But we're going to go in and actually choose which files to download. So this is what it looks like by default. And so if we look, we have no files that have been selected for download. But if we then say, oh, let's get the recommended files, we can then look at, we see that there's the CSpec and preview spec files that are available to download for the 2 targets that I selected. And so by default, the ASpec files are in our recommended products. And so what this means is that you're not going to get the fuse data when you do the just recommended products. But if you go back and select all files instead, And then if we take a look, we can see that we have the A spec, C spec, preview spec, and the level 0 spec files as well, which are the sys files that contributed to making the C spec and preview spec and A spec files. Yeah, we'll go into a little bit more detail about the specific suffixes in the walkthrough. So you'll see all of the products and stuff. But yeah, so the A spec, just short, is a budded spectrum. C spec is the co-added spectrum. Preview spec is just all of the abutted gratings and instruments. And then spec is the level 0, just sys files. They're cost level. They're just like the very bottom level contributed, but they're calibrated with, they have some sort of special Ulysses calibration applied to them. So, okay. Yeah, and then if we just wanted the A spec file for some reason, say we just wanted the fuse data, you can use this box here, which uses regular expressions. And if you're not familiar with regular expressions like me, there's a link here that can help try and guide you to how to use it. But for our purposes, it's pretty simple, and we can just search A spec. And if we select search, we see that there's only the A spec files that show up now. And similarly, if we search preview, and view the selected files, we can see that it does different behavior than what I was saying yesterday. So I think something happened. I was going to say you can download the HTML files, but now I'm not sure how you can. So that's new since last night. Okay, and then to actually download the data, what you do is you can scroll down to the bottom, and there's 2 options for flat and nested. Flat just means that it's downloading everything into a single directory, and nested means that it's downloading the files into different root names, folders with different root names for each root name. So then to actually download, you have the options for the API query, which just gets the curl things that you can then download the script or just copy directly into the terminal if you only have a couple of files that you want to download. Or you can press start download, which will download a zip folder. Okay, so one last thing that I want to draw people's attention to is that if you notice here in the target or the file name, that the target's name is sk-67d2, and this target is different than our Ulysses name, which is sk-67 2. And so we have the name that's in the file is our Ulysses HLSP name, where that file is like a very specific format that you have to have no spaces and no periods, all sorts of stuff like that, whereas the Ulysses name can be a little bit prettier formatted. And so if you go back to the edit search button, or you go back to the search form and you search for that object with the HLSP name, what should happen if we select don't resolve and we just enter that name, it should find that target. And this is behavior that it wasn't doing before because it was looking just for the Ulysses name. So we wanted to have this ability that you could go directly from the HLSPs to the search form and search for that target. But now when you do that, just be aware that you're seeing what it actually is doing is it's doing sk67 to star. And so it's getting all of the files that have 2 and then something after it. So you're seeing 261, 266, and so on. So this is expected behavior. It might be a little confusing at first, but this is just so that you can go directly from the HLSP name to the search form easily. So with that, I'll stop and take any questions about the catalog or the quick look plots, if people have any, before we get into the meat of the session. Everyone's ready to use it? Sorry, Julia.
Thanks, Rachel. There's a quick one actually about the measurements that you pull from the literature references and following Paul's comment in the Slack, will they be updated at all if a newer reference becomes available with a more up-to-date measurement, say, from these data?
Yeah, this is something that we talked about, and Julia, correct me if I'm wrong, but I don't think we're going to be updating this based off the literature, just because it was a lot of work to collect all of these, and it's just, this is what's supposed to happen, is it's supposed to get better. And so there's not a good way to go in and update things kind of automatically. But Julia, I don't know if you want to add to that.
Yeah, I agree. I would say the only circumstance when we would consider it is if somebody provides the Excel spreadsheet like with exactly the same format and columns and values that we need, then it's easy. I think you just copy paste columns, but in principles, as we said before, you know, our team is basically going to be dissolved after this workshop, which means people will be moving on to their other mission work, and so we don't really have resources to do major updates. But we can keep it in mind for the future. Yeah. Yeah.
Yeah.
Yep. Yeah, I mean, I think there's also, you know, we could post things to the website. That's easy. There are small things that we can do, but there's nothing major. Database updates are not trivial.
Yeah, unfortunately. But Will and Alex and Julia all did a very thorough search of the literature right before DR7. And so these are some really updated values compared to what we had at the beginning as well, especially for the massive stars, if I recall. But any other questions? There's one online. Go ahead.
Yeah, just on that point really about the spectral types.
You're really hard to hear.
Is that you? Can you hear me? I can change my volume.
People
But
online, the sound's too faint.
I guess I'll talk and hope you can hear. So really the issue is that the spectral types are the best from the literature, but certainly the XShootU data improves upon that spectral type information. So this is just for the OB stars in the clouds, but it's certainly soon we should be in a position to provide better spectral types based on the XShooter data for those massive stars. But it's but we appreciate that it may well be that this is, you know, we're locked in now for the database. So it's more of a, you know, whether there could be some added information provided elsewhere on the fact that the improved spectral types will be posted somewhere at some point in the near future.
Follow up, when you say soon, is that like a couple of years or several months or?
So I would say the definitive thing could be a year or more away by Jesus Meza-Pelanes, but we could certainly do a much better job than we have up to now in the next couple of months.
Thanks.
Okay, now we'll move on to the walkthrough notebook that Elaine and I will be going through. So this notebook is available on our GitHub, GitHub Space Telescope Ulysses. Okay, Joe's going to drop the link in the Slack. So feel free to follow along if you have things installed. If you don't, then ping us afterwards on Slack or just find us around the conference, and we're happy to answer questions about working with these data. So in this notebook, we're going to go through what the different types of the high-level science products that are offered by the Ulysses team. Starting with level 2, we're going to skip level 0 products. And just to familiarize everybody with the data, different data types. Listening to this conference, many of you are already familiar, but hopefully you'll still be able to learn something new about what data exists. Okay, so just to say quick too about Jupyter Notebook, if you're not familiar with it. To run a cell, there's options up here that you can do run, and you can run selected cell and all below, or you can just click a cell and click and use on the keyboard shift return or shift enter, and that will actually run the cell. Happy to help other people with Python later on too, or just ask in the Slack as well. Yeah, so first we're just going to start with importing some functions that we're going to need to look at all of the data, and then ran through this a little bit, but just a quick reminder of all of the different spectral types. Before, are people in the back, was this big enough for people in the back? Cool, thank you. So just a quick reminder that the level and the product type are listed here. Those are what I would draw your attention to. So level 0 products are end in the spec.fits format extension. Level 2 products are these cspec.fits files for combined spectrum. Level 3 are aspec files for abutted spectrum. Level 4 products are these preview spec.fits, which are also abutted, but are abutted at a higher level with more gratings and telescopes, instruments, all of that is in the preview spec files. And then we have 2 level 5 products, which are the time series products, which Elaine will go into a little bit more detail about, that are TSS and split TSS. And then we have level 6 DRC.fits files as well. And then Joe alluded to this yesterday, but we have level 7 products that will release soon that are VLT spec.fits files. Okay, so I'm first going to talk about what we're calling non-variable spectra. And so these are spectra that we looked at the fluxes, and there's no apparent variability in them, so we're able to co-opt them. And so to start, we're first going to download data from a star in the high mass sample and a star in the low mass sample, so SK67, 167, and XX-CHA. So these cells are using the curl scripts that I showed in the catalog download. And so this is what it'll look like if you just do the API download as well. So we're just going to download those files and do a quick ls, and we can see that we have all of the files that we were expecting. We have 11 different files, lots of different CSpec files, especially for XX-CHA, and that's because we've observed it in many different modes. And then only 1 CSpec file for SK67, 167. And then we also have level 3 products, which are the abutted spectrum. And we have 2 downloaded preview spec files, 1 for each target, which is what we expect. So let's first take a look at these 2 files, just using this .info when we open the file. Just quick look at what is actually contained inside of each of these preview spec files. I've totally skipped that we're first going to look at the level 4 preview spec files. And so just to get an overall idea of what the spectrum looks like for those and what those files look like. So if we look at the .info and just see what is contained in the file, we can see that there's 3 extensions in these files. There's the primary header, the science data extension, and the provenance data extension. Something to also notice is that for both XX-CHA and SK67, 167, the file structure is identical. And so this makes it easy to hop between different stars and not having to change the different formats of the files. The preview spec files are the same regardless of what category of star you're looking at. We're then just going to scroll down and look at the first science data extension. We're going to also look at the provenance extension, but we're just going to start with the first data extension to begin. And to do that, so we just open the file as we did before, and we can use this spec HDU, which was what we're calling that we opened, and we access the first extension, and we're just going to look at the columns to see what's contained inside of it. So inside of it, there's wavelength, flux, error, signal-to-noise ratio, and effective exposure time. So we're going to look at the first 4 columns, and it might be that you have a use for effective exposure time, but we're just not going to show it here. And so what that is at every wavelength, it's how much time went into that contributing pixel, basically. It's useful. We're just not looking at it here. I promise it's useful.
I'm not sure I understand the concept.
Of what?
Of the effective exposure time.
Oh, maybe we can talk offline about that a little bit. Yeah. Okay, so next let's actually open the file and take a look at it. And so to do that, we're just going to, again, access the first data extension from our file that we're opening, and then use this .data call that accesses the data section of the science extension. And so we can also use .header instead, which has a lot of useful information in it as well, such as the quality comments that Joe was talking about yesterday. So we do that for wavelength, flux, signal to noise, and error. And then we're cheating a little bit, and we're going to access the second data extension to get the grading. We'll talk about the provenance extension, but just basically, I just want to make it easier to plot and to see what we're looking at. And so we're cheating a little bit and getting all of the gradings that are combined in this particular preview spec file. And then just one other note of something to do to make it a little bit prettier to plot is that anywhere that the flux, error, signal to noise ratio is 0, we're going to set to be nan instead. This is basically just making it look prettier where there's a DQ weight in the data. So anywhere there's a serious data quality issue, the Ulysses team sets that to be 0. And so that value will be, and so that's only if there's not other contributing data that you're able to dither across and mask out in a different way and get actual data for. And then it will be 0. And so this is purely for plotting. You're able to bin it as well. Just in my example, I'm using nans. Okay, so without further ado, we're just going to plot this up. We're not going to go through how to plot it, but you can look at the details there, ask us. So the first one we're looking at is XX CHA. And so you can see that we have just one continuous spectrum here, which is what we're expecting. And so there's definitely breaks when the error and signal to noise ratio that you can see. And so this is, maybe you can't see, I don't know, but for my eye, it makes it very obvious to see that there are different contributing gradings that are going into this preview spec based off of the error and signal to noise. But overall, the flux is really great just to have one continuous spectrum without having to stitch anything together. And so that's kind of the purpose of these preview spec files. And if we scroll down to the massive star now, we can also see that that's also beautiful and great. So now we kind of have a handle of what was in the preview spec files, hopefully. So let's now look at the level 2 C spec files. And so these are the combined spectrum that we're hoping people should use for their science. So we'll open the file again, just look at the info and columns just to look. And we see that the C spec file, again, has 3 different extensions, just as before, as the preview spec file does. And it has the same columns: wavelength, flux, error, signal to noise, and effective exposure time. So this makes it really easy to use, that the files are in the same format, they have the same columns. Nothing crazy is going on with that format. So now we're going to plot the different preview spec files and overplot the level 2 products just to see how they compare. So this plotting is exactly the same as before, except we're grabbing all of the level 2 files that have this C-spec extension as well. So when we plot that up, we can see that for the XX-CHA spectrum, we have 5 different gradings that contributed to this data set. So the different gradings are colored. And if we zoom in a little bit, you can see that underneath, there's the black spectrum. It's kind of hard to see because they line up exactly, but when we get to the massive star, it'll be a little bit easier. And you can see at the transition points that this orange is a little bit lighter than this orange because this part of the spectrum did not make it into the preview spec file. And so that's part of the abutment rules that we made for the preview spec files. So if we scroll down to the massive star example, this is much easier to see that this part of the spectrum is not in the preview spec. And so, yeah. Something else to say about the massive stars is that the reason why it's easier to see here is because this black spectrum here is where fuse is the fuse regime. And so we have fuse data for this target rather than HST data. And so fuse data is not delivered as a CSpec file because it's abutted. It's not actually combined. And this is just what the default behavior of the fuse pipeline outputs. And so just to be consistent, we delivered it as an ASpec file instead. And so we're going to look at that next, just as a complete overview of the products. Okay, so sorry. For level 3, ASpec files, we open that up and we can see that, again, all of the format's the same, again, just like for the CSpec and the preview spec files, that the information's the same, should be easy to work with. And so we plot this up again, but this time grabbing only level 3 ASpec files. And if we plot that up, you can see here that for XXSHA, we now have our 5 gradings have 5 different CSpec files have been turned into 2 different spectrum, where we have the STIS low resolution gradings abutted in blue, and then the COST medium resolution gradings abutted together in green. And then if we scroll down to the massive stars, we can see that now we have the we have an ASpec file for the fuse data, but we don't have an ASpec file for the redder part of the spectrum. And that is because we only had one grading that contributed to this target, to SK67167. And so because that we are not actually needing to abut anything, we only deliver the CSpec file for that target. There's no other medium resolution grading that needs to be abutted together. So that was a whirlwind of the science data extensions. The other information is in this provenance extension, which has been put together and contains a lot of useful information of what actually went into that specific file. And so this is different for each product type, but we're going to take a look at the preview spec. In particular, we're going to look at the XXSHA preview spec just because it has more contributing columns, but the massive star SK67167 also has the same provenance extension. So you can see that there's lots of different file names, or not file names, I just read file name. There's lots of different column names that you're able to select on. Some of them will be useful for you at different times. Some of them you won't ever care about, and that's totally fine. But let's take a look at just a few that we at the Ulysses team kind of like to look at. So file name, proposal ID, instrument, detector, disperser, beginning date of the observation, and the exposure time. So you can see that these are all of the data sets that went into the one preview spec for XXSHA. And so lots of different files here and other programs or other targets. There's multiple programs that are combined together, and you can also sort by time a little bit as well. So there's just lots of useful information in this. And you can see that if you print all of them, there's all sorts of information that you can scroll over and explore on your own as well. And you're also able to just get the single column, just how to access it. If you just wanted the file name, you can just take the second data extension and put in brackets the name of the column that you want, and you'll just get the one column, which is great. And then one last note of how you might use this extension is if you were curious about what files went into this preview spec that have a grading of G130M and used the cost instrument, you can use this AND logic here to index the different provenance table extensions, and you can see that the output is now we've parted down from all of these files to just those with costs and G130M. So that's all for the COAD spectrum. We're happy to take any questions, and we're also go into this in more detail later on. But yeah, we have time for questions now, so before Elaine jumps into the time series spectrum. It's going to be very short if nobody has any questions. Okay, Joe behind you.
So I had to install the Ulysses utils for this to work.
So you should be able to just do a pip install Ulysses.
No,
and that
I
will
already did, but it was just in case other people needed it.
Oh, yeah.
And then the Matplotlib widget is not working for me.
Yeah, that was something that we weren't sure of. We've pushed a change to the repository. Joe, maybe you can. Yeah. No. But yeah, you can change this. You can comment this out with just a hashtag, and you can instead do matplotlib inline instead. Or you can pip install the package that it gives you an error with. We've added that to our package to install, but we haven't pushed that to pip yet. So those are the two options. Go ahead, Joe.
Yeah, I think this is probably easier, but if you want to fix your environment permanently, you just do a pip install ipyml, and then you have to restart your kernel in the notebook. But I think this is
Oh,
a
yeah,
lot
here.
simpler. Yeah, there you go.
Look at us, right? Neither did I, clearly.
Also, if you're not checking the Slack, so the way that the notebook looks when Rachel's running it here with results and the cells and plots and things like that, I just created versions of that as HTML files and put them on Box. So if you want a version that actually has the notebook executed so you can look at things, go ahead and download that.
You can ask more questions on Slack as they come up.
What was that? That's okay. Is this mic working? I think so. Okay. You can kind of hear me now. Hey, everyone. My name's Elaine Fraser. Like Joe said, I'm a part of the DP team for the whole time Ulysses has been going on. And I did a lot of work on the time series products, so I'll be telling you a little bit more about how to look at those files. Let me find the spot. I also just wanted to say thanks for sticking around, and feel free to interrupt me if you have questions or if I've said anything that doesn't make sense. I'm not a researcher, so it's been really cool just to hear how y'all are using our data. So, with that being said, go back up here and get started. So yeah, as Joe and Rachel have said, our time series spectra are level 5 data products, and we have these data products available for all T-Tori stars. I see now that there is a typo right there. That's great. We've edited this so much, except for that. So yeah, we make these products from the Las Cumbres Observatory LCO data, as well as the HST spectroscopic data, and there's lots of different combinations of the output products that we can get based on the T-Tauri star type, whether it's survey or monitoring, and which data we're using, the LCO versus HST. So for the survey T-Tauri stars with LCO and HST data, we only output exposure level products, so this is just taking the data that is used, you would get it, and stacking it together to make the time series product. But for the monitoring stars that have HST data, we also make sub-exposure level products. So since we're using cost and just time tag data, we can break down the events as they arrive at the telescope into smaller time bins than the actual exposure time, and then create sub-products from that. So that's what we're calling the sub-exposure level products. And we only have those for our monitoring stars, of which there are 4, and the HST data for those. Cool. Okay, so I'll just start by going through the FITS file structure. This is all very similar to what Rachel has shown already for the non-variable spectral stars. The data is stored in FITS files in 2 bin table extensions, the science and the provenance. We're going to start just by looking at an exposure level time series product for TW Hydra, one of the monitoring stars, but this one's going to be made from the LCO data, which is kind of in a different format than a normal spectrum that you would look at. So we'll download this file using curl, and then just make sure that it's downloaded here. Yep. So just to note, like Rachel said, the suffixes at the beginning, this is a _TSS for the time series spectra, so you know what you're looking at. So we'll just go ahead and make a path here and open the file and then do the hdu.info to see what this looks like. So again, we've got the 0th extension, which is the primary HDU that has all of the good header information, and then the science and the provenance again. So we can just look through the file name here and see lots of good info. I always thought it was cool how we named the files, so you don't have to open up and look at the header to see everything that's in the file. One thing I did want to point out is the LCO GT is the former name of LCO, so you'll see that in our file name still, but it's just referring to LCO. And then the last thing I was going to point out is that since the LCO is imaging data, we only have the optical elements of these bands that we've imaged in, and you'll see how that shakes out when we open up the science extension itself in a little bit. So next we'll go through the science table. So this is the first extension, so we just open the HDU with the 1 here, and we can print out the columns. And then I'm going to show explicitly the shapes of the flux arrays here. So the flux and the error are going to be the same shapes. So this is where we can see the differences between the single epoch or the non-variable products and our time series is that we now have multiple rows that correspond to all of the different time bins. So instead of just a flux and a wavelength, we've got a wavelength that corresponds to all of the fluxes, but the flux itself is now a 2D array, and each row in that array is going to correspond to a different time bin. So we can see for this, TW Hydra was observed 507 times. And then the odd thing here is the number of spectral bins. This is only 3, which is unusual for a spectrum. But again, this is because this is imaging data. So I don't know if it's been explicitly said about the LCO images, but they're taken over 4 epochs before and after the monitoring of the HST T-Tauri stars themselves. So when we look at the plot of this versus time, you'll see some data that's taken before, some data that's taken after, and then some LCO data that's taken at the same time as the HST monitoring data. And these are going to be taken in 2 or 3 different bands of the SDSS U prime and I prime filters, and then the Bessel V. So this goes back to why there are only 3 spectral bands, because this one was only observed with the 3 filters. So just to be super explicit about this, we'll just print out the wavelength array here. So you can see the U prime is the 3560, the Bessel V is the 5450, and then the I prime is the 7670 wavelengths. And then printing out the flux, we can see it's basically like a 2D table. Each row here corresponds to a different time bin, and then each column corresponds to the different wavelength arrays that were observed at that time bin. So getting ready to plot this now, because there's only 3 wavelength bins, we're going to plot flux versus time instead of flux versus wavelength, as you would for normal spectrum. So I'll just call out this using this list comprehension, like explicitly pulling out the fluxes for each wavelength instead of having this format here. Just makes it a little more easy to comprehend that. And then I'll skip over the details mostly of the plotting. We're just doing a scatter plot. But I did want to point out there's this really cool package in AstroPy. It's just astropy.time. And if you give it like an MJD, which is the format of all of the times that we've got in these files, you can reformat it to be ISOT, which I don't know what that stands for, but it's a lot prettier than an MJD date, so I will just say that. So go ahead and plot this up so you can see what this data looks like. So we've got the exposure date versus flux, and then the different colors correspond to the 3 different wavelength bins. And I was just going to say it's kind of a happy note the way these colors came out by default, because they kind of correspond to what you would think of by eye. So the blue is the U prime, the V, or the green is the Bessel V, and then the orange are the I prime data sets here. So you can see the variability in the flux. And like I said before, each of these are observed before and after the HST data for the monitoring stars. And then for TW Hydra, we took 2 different epochs. So that's why there's like 2 groups over the course of almost a year and a half, I guess, for this data set. Okay. Are there any questions about that? Before you look at the provenance data? Yeah, Will? Have we found a bug?
I was just saying the I-band photometry shouldn't be 0, so we track down why that happened.
Yeah, I thought maybe it was just a plotting thing, and I did try to plot it in log space, thinking that would pull some stuff out, but I think it was also 0, and then I just kind of moved on. Sorry, guys. We'll work on that. Thanks, Will. Okay. I'll quickly look at the provenance extension for this again. So we can pull out this just looking at the HGU, the second extension, and you can just print it with the columns. So these are all very similar to what we saw before with the non-variable data sets. I think the biggest thing here that's different are the MJD beginning, middle, and end, which can be useful. So I'll go ahead and print out what this looks like. Here's some of these. So we've got a row here for every time bin, and you can see which filter was used, the exposure time. So you can see the common exposure times we use for all of the different filters for these, and the file names if you're interested in going to look at the LCO data itself. Okay, and I'll go ahead and close that file. And then I'll start on the sub-exposure level example. So this is also going to be for TW Hydra. Download this. It takes a little bit longer. Live programming. That's good. This one's really big. It's got a lot of rows in it because it is the sub-exposure level example. So again, we'll look at the just the info about the HDU. Very similar, like we've seen before, the primary science and provenance and extensions. And yeah, this is still a level 5 data set, and the suffix here is the split TSS this time because it's denoting that it is a sub-exposure level data product. Okay, so we'll look again at the science extension and then pull out the shape of the flux array. So very similar columns, flux and its error, wavelength, and NJD start and end. You can see the number of time bins is a lot longer this time, and there's lots more spectral bins, which is what you would imagine for an actual spectrum this time. So we'll also just look at the provenance data really quick before we get into the pretty plots of this. This is all very similar to what we've seen before And again, with the MJD start, beginning, and end. I guess the thing to note for these type of files is that the file names here are going to be the same because we're splitting one file into multiple entries into this data product. So you can see that the bidding that we used for this was to break the exposure time down into 30-second chunks. And for this, sorry, I keep doing that. For this file here, the exposure time, I think, was 300 seconds. So each file that we've observed has now been split into just 10 different sub-time bins and has been put into the file now. So that's why that time bin array is so long. And you can also see the proposal ID. We took these over the 2 different epochs here and the different sim waves that were observed in and stacked together for this data product. Okay. Cool, so now we'll get into the plotting of this file. We'll actually look at flux versus wavelength this time. Again, turning the MJD starts and ends into pretty formatted dates and times instead of the MJDs. And because there are the 720 time bins, we're just going to pick out some random indices and plot the spectra that are at those times. So I've chosen just randomly the beginning and end time, and then a few in the middle so that we can see what these look like. And I'll also note that I've zoomed in here on carbon-4, because everyone loves carbon-4. You can barely see that at the bottom here. So yeah, like I said, flux versus wavelength, and each of the different colors corresponds to a different time that the spectra was observed in. So looking at the variability, you can see over the span of, I guess, almost a year and a month or so, that the flux has gone from, I guess it's tripled almost and then gone back down over the course of this time that we've been observing it. And then just wanted to point out, looking at a shorter time scale now, this is just going to zoom in on some indices over the course of a single day. So this is the same exact plot, except we've changed the indices that we're looking at here. And if you do get the widget working, you can use these cool little tools to zoom in a little bit. We're still looking at carbon-4. So you can see the dark blue here is the very first indice, which is April 2nd. It starts at the low flux and then goes to green, which is a little higher, then orange, then pink, and then peaks with the yellow. And then just over the course of a few more hours, it drops back down to the dark blue, or sorry, the light blue spectrum at the bottom. So all of that variability, it was over the course of a day, which is pretty cool. Okay, I think that's all I wanted to say about the time series products, but I'm happy to answer any questions that you've got before I move on to the drizzled images. I'm going to take a sip of water. Okay.
How many people are following along on the Python notebooks?
Do you have a question?
Just very simple. What does the last line do? I mean, it closes.
Yeah, so there are different ways to open FITS files. Let me scroll back up to the beginning where I've opened it. So in Rachel's examples at the beginning, she used a with statement, which will close a FITS file just after you're done with the with loop. For my examples, I'm not sure why I did it like this, but I just do fits.open and then the file name. So it's like the HDU is open the whole time, and then at the very end, you'll want to close it again.
Yeah, okay, it's fine.
Yeah. Yeah, you're welcome. Okay. So I'll quickly go through the WIFC3 drizzled images. These are all level 6 data products, and we've got these only for 2 galaxies, the NGC 3109 and Sextans A. These were taken before the spectroscopic observations were done so that we could do SED fitting and get accurate exposure times for our spectra. But since we had them, we thought, why don't we go ahead and have these be data products too? So these are a little different because they are images. So if you've never worked with drizzled images before, which I have not, I will freely admit, they come out looking kind of similar. So there's a science extension still, and then there's also going to be a weight map extension. And then the last is a provenance extension again. So let me go ahead and download this. I think this will also take a little while. Twiddles thumbs, maybe. Yeah, these are beefy, sorry. I don't know if I can pause it and just keep going. Okay, well, we already have these downloaded, so we'll move on. Maybe not. Live coding. Bummer. Okay, sorry guys. I will download the real thing. I know, I just tried to cheat the system. What? Yes, so I'll go ahead and say this file has the DRC extension at the end, which is a CTE-corrected drizzled image. Comes out for all of the WISC3 data, and we can see like what filter it was observed in and all of the good target information. And now it is done, and we'll do this again. Okay, so you can see, like what I said, the primary extension has the header info, and then the science, and then WHT is the weight image, and then the provenance extension at the end. Okay, so I guess one thing I was going to point out that's different here is you can see it's different because the type is not a binary table HDU anymore, it's an image HDU. So when you just look at the shape of the first science extension, you can tell it's like roughly a square that you would imagine you would get from an imager. And then we can go ahead and plot this up. One cool thing I wanted to point out is this AstroPy WCS module. And you can just feed it the header information from the file itself, and it pulls out the RA index and the position angle and stuff and makes a cool WCS object. And when we put this into the subplot and just say the projection is this WCS thing that we made, it makes the plot look really nice in RA and DEC, and have the rotation as you would expect. This also takes a little while to plot up here. This is what this file looks like. So you can see our pretty galaxy down here, and in the middle here, I believe, is the chip gap. And you can see this a little bit better when we look at the weight extension that we'll talk about next. So again, if we just look at the shape of the weight extension, it's going to be the same as the image itself in the science extension. And we'll plot this in a very similar manner using the WCS again. Give it a little time. Okay, so this is what the weight map looks like here. So when we look at the provenance, you'll be able to tell this better, but 2 images were drizzled together to create this. So the units of the the weight map here are basically, it's kind of like the effective exposure time we were talking about before. So it'll tell you each image exposure time was about 450 seconds. So when you look at the little box that comes up right here, when I hover over it, you can see like the effective exposure time that went into creating the file itself. And you can better see here where the imperfections are and where the 2 images kind of like slightly overlapped, but are kind of truncated at the end, at the top and the bottom. So that's what the weight map looks like. And then just briefly look at the provenance table. It's very similar as before. We'll pull out some of the cool columns. So you can see which filter was used and the aperture and the exposure times for both of the files that were drizzled together here. So I think that's all I wanted to say about that, and close the HDU at the end. And this is the end of our walkthrough. So we're happy to take questions about any of this that we just went over, but I think next Joe is going to advertise some of the other notebooks that we can talk through on Thursday. Is there questions? Okay.
Yeah, so I'm kind of new to this, but on the weight part, so trying to understand the kind of what does the weight do in this case?
So it basically, I'm sorry, I don't think I described this very well. It kind of takes into account the DQs for the images put together. So when you look at the weight versus the actual science image itself, you can see where the weight is 0, the flux in the image itself has gone down to 0 too. So it takes into account all of the imperfections in the detector and the exposure times of the data that were stacked together to create the final image here. Does that make more sense?
So, for example, the line in the middle is that it's not good data.
Yeah.
Is it the center of the lines? Like?
Yeah, I believe that's where the chip gap is, but I don't quite know exactly because I would expect it to be like a solid strip where it goes to 0. So I'm not sure why it looks like more pixelated. I don't know if anyone else has a good answer to that question, but yeah, I guess it's just one exposure. Well, it's 2 exposures that are drizzled together. So it's like
that's with
every
two
other
lines.
pixel.
Okay.
Okay.
Right.
Okay. Thank you.
And so the image below is just changing the value of the weight, or like the next image after that one. So that's just changing the values of the weights for or what's happening in this case?
I think it's showing for each pixel like like which pixels went into the final drizzled product itself. So where it's 0, there is 0, like neither of the images contributed to the final product versus like up here, it's like only one image went into the final product, and at the bottom, just because of like where the pointing was. Yeah, the dither on purpose, I guess.
0, 1, 2. Okay. Yeah, something like that.
Yeah.
Yeah. Yeah. Okay. It's kind of misaligned. Okay. Thank you.
Thank you. Those were good questions. Okay. Thank you all.
Who was able to follow along and get to the end? Yeah, that's pretty good. All right, excellent. And now you have some notebooks for posterity if you ever need it for your work. Play with the time series or the coads. Even, our team is going to disappear, so we won't be updating any of the HLSPs. But in the future, if there are some new calibrations on the spectrographs, you can just re-download the Ulysses data and rerun all the HLSPs and get all the calibration updates in your data. So that's kind of the point of the session, is to train you all to be able to do this when we're not here anymore to do it. I mean, we'll still be here just doing other things. So, thanks a lot. Joe, Rachel, and Elaine.
Yeah, a little bit.
Oh, yeah.
Okay.
Sorry.
I actually only budgeted like 5 minutes for this, so I have a lot of time. Rachel, how can I see what's underneath that? Oh yeah? Ah, Okay. Okay, so in the last few minutes, what I had planned to do was just showcase the other notebooks that we didn't run through. I'm not actually going to run them, but I just wanted to make you aware of them so that if you want to know more, we could spend detailed time at Thursday's parallel session going into those, because those are a little more in-depth. This was like a walkthrough, high-level overview of the products, and the other notebooks show you how to actually create the products from scratch. So, okay, you already have them open, Rachel? But this is like GitHub. Oh, okay, I see. All right. No, this is fine. Okay, I'll start with maybe the most useful one. Is using our Ulysses co-addition algorithm. So this notebook will show you how to recreate a Ulysses product using the co-addition algorithm, which is what Julia just mentioned. Even though we won't be delivering updated products and new DRs, some of you may know the cost team is in the process of updating the geometric and walk correction for the cost detectors. That's going to give you a really improved accuracy on the wavelength scale. And so whenever that's available, you could re-download the cost data sets for, I don't know, a massive star of your interest, and then re-coad them to create versions of our products. So this will show you how to do that right here. It will also show you how to create co-added spectra for non-Ulysses data. So if you just want to use our algorithm on any spectra, this should work just fine for HST costs and STIS data. And I should work for fuse data, but that's about it. It's only designed for Ulysses products. So yeah, I'm not going to run through this, but if you do want to see this like in real time, like post in the Slack or grab one of us and tell us, and we will run it on Thursday for you and show you how to do this. Otherwise, you can just peruse it at your own leisure. Okay. Another notebook we have here is how to create our custom calibrated STIS spectra. This is a little more complicated because to do so, you need to supply, maybe you remember I mentioned this yesterday, a YAML file, which is this configuration file which tells the Ulysses code how to perform a custom calibration. Like, do you need to do a custom extraction? If so, what's the Y location of your source? What's the size of the extraction box? Where's the background regions? Things like this. So for stars that we've already done that for, it's all available in this package. You don't need to download it. But if you wanted to do it on your own STIS spectra, you'd have to create that YAML file yourself. And there's a little bit of information here on how you could do that. But we also show you how we do it ourselves for one of the stars in our sample. Okay, and this is information on how to do programmatic downloads of both the Ulysses data products. So it's a little different than what you saw Rachel and Elaine do. They were just executing curl commands, which is something you can run on the terminal. And in Jupyter or Python or anything like that. This notebook actually uses the Python package AstroQuery, which is created and maintained here in-house to query different astronomy catalogs, including MAST. So this shows you how to use the API for that package to download our products. It also shows you how to use our Ulysses package, the utilities package, to retrieve PIDs, that's program IDs, for Hubble data that contributed to specific Ulysses targets. I think in this one we show you like all the program IDs that contributed to LMC targets and so on and so forth. And then how you could download those data again. And then finally, you saw a really good introduction to this today about the provenance extension and our products and how it lists the input files that contributed to a product. You can use that information to figure out what we call the constituent data sets. So say we co-add 4 cost spectra to create a co-added product. you can work your way backwards, determine what those 4 individual cost spectra were, and then download them again using the Astro Query API. Is that it? Oh, one more, okay. And then the last one, again, this is a little more complex because you have to supply one of these configuration files, but we do show you how to create time series spectra. In this case, we're just showing you how to create exposure level products. To create those sub-exposure products is actually quite a bit more complicated and maybe beyond the scope of what an external user would be interested in, because you have to split them up into those sub-exposures, like Elaine said. That involves running 2 different CalCOS routines that are extremely time costly. And so in this case, we just walk you through how to do the exposure level ones, or you can stitch together individual cost exposures and put them in that 2D array that Elaine was showing, which basically stacks spectra. And there's a little bit of information on how you can do this yourself by creating, again, these configuration files that's required to run the code itself. Okay, so yeah, that's really just, I wanted to highlight those. We do have 8 extra minutes, so we can take questions about any of these topics which I just talked about here, or anything that you heard about today. Questions about the data, how to use it, how to get it. This is your chance. You have experts here who were involved in the creation of these products. There's a question over there if you want to run. The other mic here? Okay. You 2 might need to grab it if something comes up.
Thank you. I have 2 questions. So you mentioned you also have algorithm that deal with fuse spectrum. So is there like a notebook that's published that we can follow through?
In general?
Yeah.
Or we do have notebooks that show you how to correct the fuse spectra that we found had problems. Do we use fuse? We don't use fuse input data for any of these, I don't think. None of these examples have fuse data, but it could be added if it's something that is interesting and useful to the, our users.
Yeah, because I think like a lot of the massive stars have fuse spectra. Yeah. I think I'm just genuinely interested in how those are being produced.
Yeah. Okay.
Yeah.
Oh, we can look into it. Yeah.
Yeah. Sounds great. The second question is, so for the COS and the STIS, these are designed for stars. Does it matter, say, if I want to do a quasar?
For the co-addition algorithm, no, it will not. It's arbitrary. You're just using the flux-weighted average method that we devised. Mm-hmm. You can give it any kind of. In fact, personally, I have actually used this co-addition algorithm on AGN, so it works. Okay, but you can do it on whatever, as long as it's COS or STIS data.
Okay, yeah. Thank you.
I would add, of course, beware of variability. If your AGN is variable, I mean, you get out what you put in, right? So.
Thank you for the questions. You want it? Oh, you want to show the... Okay, you want to do this? Jan? Here, stick this on you. Oh, gosh.
I'm just going to hold it. I just wanted to give a quick preview of the Penelope and XShootU data, because I know that was a question yesterday as well. Bigger? More bigger? Okay, so first I'm just showing this is just the structure again, so just doing the .info and then .columns. And so for the Penelope data, you can see that we've stacked it into each epoch and each arm of the telescope is in a different extension. So we've just taken all of the input files and put it into a different extension for each of the data sets that the Penelope team provided us. And then the XShootU data, they actually provided it to us in this format already. So we didn't have to do that, but it's the same format that each, there's only 2 arms here. That's why it confused me at first. Each epoch is a different extension, and then each arm is also a different extension. And then the data columns, the XShootU data has a lot more columns. That's just what's in their data. And then the Penelope data has wavelength that we changed to just make it obvious that it's the air wavelength and not the same wavelength scale that we have in the HST data. So just wanted to give a quick preview of that as well. They're not available, but we'll hopefully update the notebook once they are to include the level 7 products as well.
You three, yeah, that was great. Hopefully helpful to everyone. Save those notebooks. I just had a couple of announcements to make. Tomorrow there's a dinner at 6 p.m. at Gertrude. You should have received, if you determined to go in your registration form, you should have received an email from Sharita asking you for your meal options. So please reply. And then on Thursday, reminder, we have some kind of more open-ended hack sessions, one on hub worlds. We could possibly go into more details on the data products too, if people want to, the folks who weren't able to follow along with the Python notebooks, download, try it at home, and then if you have any questions, we can go back. Also, if you have your collaborators here and you want to do a collaboration meeting, we can support that. And so if there are any requests for such hack sessions, then please email us and we will get it set up. But it's already Tuesday night, so I just wanted to remind you Thursday is like just around the corner. And so I don't have anything else, and so we can reconvene tomorrow at 9 a.m. All right, thanks everyone. See you tomorrow.